Okay, today we're going to be talking about periodic trends, and we're going to be looking at them from a new lens. We've already actually discussed periodic trends before, but we want to look at them from the new lens of valence electrons that we've talked about in the past. And this is especially for 6th period who didn't actually get this discussion. So, ionization energy. Ionization energy is equal to the amount of energy needed by the atom to lose an electron. So we're talking about all those atoms that are going to lose electrons. The lower the ionization energy, the more easily an atom loses an electron. According to what we know about valence, which family would you expect to most easily lose electrons and why? So think about that for just a second. Which family, based upon what you know right now about valence and ion formation, is most likely to lose electrons, and why do you think that? So now, according to what you know about valence, which family would you expect to resist losing electrons, and why do you think that? Now, the reason I'm asking these questions ahead of time is because we're going to be looking at the graph in just a second, and we're going to see if your predictions based upon valence are correct. So here we go. We're going to be looking at the graph now. So here's the graph, and what do we see? We see very clearly that lithium, sodium, and potassium are the lowest in ionization energy, and that's kind of what we expected. We expect that these that have a single valence electron would lose that valence electron more easily to become like a noble gas, and that's exactly what we're seeing on our graph. We also see that helium, neon, and argon are highest, as well as krypton over here are highest. And that makes sense as well, because we know that they have full valence shells, and we know that they want to keep all of their valence electrons. So that makes a whole lot of sense to us when we think about it in terms of valence. So this graph makes complete sense. Now, I want to look at these areas right here. These areas right here, and I want to look at them in terms of electron configuration. So I'm just doing these, and remember, P's have 3 orbitals, S's have 1 orbital, right? So beryllium looks like this when I draw its electron configuration. That's beryllium. And then when I add one more electron in, we see that that's boron's electron configuration right there. Boron's electron configuration. Well, what does this part of the graph tell you about that single electron that we just threw in for boron? Well, according to the graph, it's more easily lost than beryllium's electron. So when we're looking at that, we can see that there's a reason why Pauli knew that I had to put one electron in first. So if we look to the next jumper, we see a similar pattern. We see nitrogen and oxygen. Well, nitrogen's electron configuration looks like this. For oxygen, we come in and we add one more lonely little electron. Well, we can see very clearly, well, adding that one lonely little electron that doubles up one of those orbitals causes oxygen to lower its ionization energy, meaning that electron wants to be lost, because having an electron configuration like nitrogen is better than having an electron configuration like oxygen. This is what Pauling knew when he was doing this electron configuration. Remember, we talked about the fact that we put one electron in each first and then double up. This is how he knew this. He knew this based upon the information that we were seeing on the ionization energy that was coming up. So pretty interesting that we can see that from the graph, and after having looked at it from the perspective of valence and electron configurations, we now understand where all of this is coming from. So if all elements lost the first electron, so all of the elements have lost their first electron. Now let's think about that. All right, everybody's lost one electron. Which family would you expect to most easily lose an electron now, and why? Now I'm going to tell you, it's the same reason as it was before, but it may not be the same family. Second question is, which family would you expect to resist losing an electron now, and why? Again, probably the same reason it was before, but it may not be the same family. So let's look. What does our graph tell us? Well, we can see very clearly atomic numbers 4, 12, and 20. 4, 12, and 20 are in group 2. That's beryllium, magnesium, and calcium. Those are the ones that we have going on there. And now the highest are 3, 11, and 19. That's group 1. That's lithium, sodium, and potassium. Well, why did the change occur? Well, if we think about it, we completely understand. Now, group 2 are the ones that only have a single valence electron left to lose. And group 1 now look like noble gases because they lost their single valence electron. So the answer is the same. It is one valence electron needing to be lost for the lowest and full electron shells or stability for the other ones. So if we go to the third one, let's assume all 2 electrons are lost. So 2 electrons are lost from every atom. Which family would you expect to most easily lose an electron now, and why? And then the second question, which family would you expect to resist losing an electron now, and why? So remember, the cases were the same. So I wonder if that's the same now. Can you predict? I think you can. So here now we have, let me change color so we can see it. Here we have 5 and 13. Hey, that sounds like group 3, boron and aluminum. And up here we have 4, 12, and 20. And that was definitely group 2. That's beryllium, magnesium, and calcium. So we can see that there's a lot of interesting stuff going on here that we can predict based upon our understanding of valence electrons. So we know something right now. We know that we can predict the elements that are going to have the lowest first ionization energy and the ones that are going to have the highest, just based upon valence and some information that we can see on the graph here. Now I wonder if we looked at all 3. What do you notice when you look at all 3 graphs together? Let's see. There are all 3 graphs together. We notice a couple things. One, they're all the same shape. Relatively speaking, they're all the same shape. We also notice that we start losing electrons. So right here we have 1. But we don't have a 1 here. Here we have a 2, but we don't have a 2 here. Why? Well, because element 1 only has 1 electron, element 2 only has 2, so by the time we get to the red line, we've already lost the 2 electrons for element 2. We also notice we see the same trend. So as we go across the period, the trend goes up. As we go down the family, the trend goes down, and we can see that trend in all of the graphs. So you can see, even though we're talking about ionization energies in 1, 2, and 3, we can see the same trends. Now we also see one other thing. By the time we get to the third electron being lost, what does the energy look like? Well, we can see it's so much greater. Look at that, 12,000 kilojoules versus somewhere about 1,000 kilojoules. So we go almost 12 times the amount of energy to lose that electron when we increase the number of electrons lost. So in reality, there is a limit to how many electrons an atom will lose. 3 or 4 is probably very close to the limit. We're getting very close to that limit right there. So let's look at the other 2. Electronegativity. Electronegativity is the measure of how much an atom wants to gain an electron or wants an electron. I call them electron hogs. So if something is electronegative, it really, really, really wants electrons. The higher the electronegativity, the more likely an atom is to gain an electron. So the higher the electronegativity, the more likely an atom is to gain an electron. So noble gases have no electronegativity. That doesn't mean 0, it just means they have none. And I think we can predict why. They don't have any electronegativity because they don't want any more electrons. We kind of get that. So according to what you know about valence, which family would you expect to most easily gain an electron and why? And then finally, according to what you know about valence, which family would you expect to resist losing or gaining? That should be gaining right there, I'm sorry. Gaining an electron and why? So let's look at the graph and see if we've come up with the right predictions. So the ones that will most easily gain electrons, where do you think those are going to be? Think about the valence. The ones that will resist gaining electrons, think about the valence. What do we need to know? So here we go. We've got fluorine, chlorine, and bromine. That's group 17. Group 17 has the highest electronegativity. They want electrons the most. And that makes complete sense. They have a valence number of 7. If they add 1 electron, they get to 8 electrons. So that makes complete sense to us. So the others should make complete sense too. We have lithium, sodium, and potassium. Well, they have a valence number of 1. Gaining an electron does not get them where they want to be. So they will resist gaining an electron as much as possible. So you can see everything with high valence numbers, 5, or greater are higher. Everything with low valence numbers, 3 or smaller, are lower. So this kind of makes sense as well when we think about it. Now, the next one, atomic radius. Atomic radius is the measurement of the size of the atom. So what do you wonder after looking at the graph of atomic radius? So there are a few things that I wondered when I first looked at this graph after I understood valence. So here I am, I'm looking at the graph and I'm seeing, okay, lithium, sodium, potassium. Potassium is bigger than all of them. How can I explain that? Well, let's see. Lithium is in energy level 2. Potassium is in energy level 4. Well, we know something. If the nucleus is here, energy level 1 is right there. Energy level 2 is right there. Energy level 3, energy level 4. So hang on. As I go out in energy level, I get further away from the nucleus, which means that the electrostatic pull that the positive charge has on these electrons is much less as I get further away. And that's absolutely the case. So as we get further away, the atom gets bigger. So right now we can predict the element that is going to have the biggest atom on the periodic table according to what we're seeing, and that's going to be francium, because we can see the biggest elements in the periods are the ones that are first. Now that probably brings another question to mind, and that question is, why is the first one in that period the biggest and not the last one? Because I can keep adding electrons, so I should get bigger, right? Well, remember, as you add an electron, you're also adding a proton to the nucleus, which means there's more electrostatic force pulling in the nucleus. So if there's more electrostatic force pulling the nucleus and you don't put electrons further away, then those electrons can be pulled more tightly. And so what we're seeing here is this idea that more protons and more electrons pull together more tightly. There's a stronger pulling force. Remember, a force is a push or a pull. In this case, opposite charges pull on each other. So they pull together. More of those charges opposite each other pull greater on each other. They pull harder on each other. So that is basically the view of atomic or periodic trends using valence. And now we have a better understanding of what's going on. We have a better understanding of why that is, just because we know more about valence. So we just finished there, but let's look at this graph that we see right here, this next diagram. And you can see very clearly here that we have bigger atoms here and smaller atoms here. And we can see that all the way across the periodic table for the first 5 periods. And so this is just another way of looking at what we just talked about, how as we add more electrons, we also add more protons, means more pulling power. And you can see some things that you might notice and might want to talk about later. So thank you very much. We'll talk to you later.